I'd like to explain the kernel method as of just in the second day. So probably I don't have enough time to cover all the slides today, so I will talk about support vector machine first and their approximation second, and if time allows, I will quickly explain their structured data. But perhaps I will little bit about the structured data. Okay, so in the first half, I will explain support vector machine, which is the most popular and method in the kernel methodology. And before starting the support vector machine, I will review yesterday's content quickly. So we have talked about the the kernel method, and the kernel method is basically considering the linear linear statistical method on the feature space after mapping the data to the feature space by the feature mapping. And they are representing the feature vectors, and typically in many data analysis, what we need is their inner product, computation of the inner product. That's a very important part in many data analysis. And in kernel method, the inner product of the feature vectors is simply given by the evaluation of the kernel function like Gaussian kernel. So that's quite easy to compute. This is called the kernel trick. This is one point. And another thing is that the solution of some target is typically given by simply the linear combination of the feature vectors. So the feature space may be infinite dimensional, but the obtained objective function can be reduced to the finite dimensional problem. That is the second important point in kernel method. And this point is called the representer theorem. And after recognizing that our solution is given by the linear combination of the feature vectors, plugging this form into the original objective function gives the objective function written by the Gram matrices. And after this point, what we need is to solve the problem in the standard Euclidean space. Okay. And the support vector machine follows this general idea. However, in the case of support vector machine, the method on the feature space is already new. It is not a classical statistical method, but the support vector machine on linear spaces was already new in the proposal. I'd like to explain it. So the problem to solve is binary classification. And we have, for simplicity, I consider the Euclidean space, m-dimensional Euclidean space, and we have n data. And we have, in binary classification, we have class label for each data point, data vector, and it is represented by +1 or -1. So these circles represent the +1 part, and this close parts are representing -1 part. And we want to draw some hyperplane to separate two regions so that the labels match with the regions. This is a plus part, and this is the minus part. And the most basic classification boundary is given by linear classifier. Linear classifier is simply given by the linear function. W is a weight, W transpose X plus B. This gives some affine hyperplane in the m-dimensional space. And the plus part and the minus part are separated by this function. And we want to have some classifier so that, basically all the points are classified to plus or minus correctly. So in this lecture, I just talk about the binary classification. And the basic support vector machine consider binary classification. But I forgot to include the important message in the slide. So I want to emphasize that support vector machine can be extended to multi-class classification also. But for the time constraint, I discuss only the binary classification in this lecture. Look at some standard textbook to the extension of multi-class classification. Okay. So in the most basic support vector machine, we assume that two classes are linearly separable. So that means that there is some hyperplane to separate plus part and minus part correctly. So once we know that there is at least one such hyperplane, typically we have many such hyperplanes. This is also separating two classes correctly, this one also, and so on. So in this case, you can see that there are infinitely many such hyperplanes. And the question is which is best? And support vector machine introduce some criterion to pick up one of them as the best one. The criterion, there is one, the one. The criterion is called large margin criterion. Large margin says that maybe I should explain it in the next slide. Large margin classifier requires that distance between this separating hyperplane to the nearest points should be maximized. That's the meaning of large margin criterion. And the margin refers to this distance. Well, this may be this supposes that this is a largest margin. But if we draw this hyperplane, this is also the separating hyperplane. But in this case, the margin is measured by this distance. This is the nearest point to this hyperplane. So the margin here is smaller than the margin given by this hyperplane. And by looking for such largest margin, we can pick up on one of the separating hyperplane among all the linear separating hyperplanes. And the support vector machine is called as such by the fact that in considering the separating hyperplane, we have some data points lying on the hyperplanes to give the margins, right? And that's why this is called support vectors. And I will come back to this point later. Okay, so our criterion to pick up the hyperplane is largest margin. And the question is how to solve it mathematically. In considering the hyperplane, we should notice that the hyperplane is basically given by the hyperplane given by this W transpose X plus B. And the hyperplane, this is better, sorry. This hyperplane is given, W transpose X plus B is equal to 0, right? This one is given by the equation that Wx plus B is equal to 0. However, any positive scalar multiplication gives exactly the same hyperplane and the same separation of the two regions, right? Plus part and minus part doesn't change at all. So we need to fix this to find the W and B. They are what we want to obtain mathematically. But to find them, we need to fix the scale because of the ambiguity of the positive scalar multiplication. To fix scale, there are many ways to fix the scale, but the convenient one in developing the support vector machine is this. So we have a support vectors here, the nearest points to the hyperplane. Let's say that this hyperplane, which contains the nearest one, is given by wx plus b is equal to 1. Well, if this 1 is fixed, the scale, and the negative part, this black point, well, this hyperplane containing this blue one should be, nearest blue one, should be given by wx plus b is equal to -1. In this way. This fixes the scale because the scalar multiplication changed this scalar, right? 1 and -1. So in another expression, so all the red points is in the region that the wx plus b is greater than 1 or equal to 1. And the blue one points is in the region that wx plus b is equal to -1 or less than 1. That is a way of fixing scale about w and b. And if we fix the scale in this way, it is not difficult to see that the distance between these two hyperplanes is equal to 2 divided by the norm of w. W is, well, basically this w, right? Weight vector to define the affine space. Yes?
Is the min a max, or is it
yes, max. Sorry, this is should be max. All of these values should be negative, so this should be max. Thank you. Yeah, this is a very elementary geometry, so I leave it to you as an exercise. But if we have two hyperplanes given in this way, the distance between two hyperplanes is given by 2 over the norm of W. So this is the margin. And the support machine picks up the hyperplane so that this margin is maximized. So the objective is like this. We want to maximize this margin. 2 is not important, so 1 over W, norm of W. And the constraint is here. All the points in the +1 class should take the value equal to 1 or greater than 1. And their -1 class have this different direction, equal to -1 or less than 1. And well, this is okay, but maximizing 1 over W is a little bit awkward, and perhaps minimizing the opposite W, norm of W, would be easier. And instead of norm, if we take square, this is differentiable function, so it seems much easier. So finally, our objective function is to minimize the squared norm of W. This is just a quadratic function. And there's a constraint that given by these two types of inequality. And they must be satisfied for all data points, I. I is the index of the data point. Yeah, they look like two types, but a clever way to express them in one inequality is multiply y here. And then everything can be written in this way. This is just a little trick, but well, mathematically more beautiful. So people use this expression to define the constraints given this one. And this is our objective function to solve support vector machine. And their function to minimize is simply the squared norm of W. But we have constraint about W and as B in this form. And X and Y are simply given by data. And they are, the left-hand side is simply the linear function of W and B. So we call this the linear inequality. There are n is the number of data points, n inequalities, but each of them defines some inequality given by one side of hyperplane. Okay? So this type of their optimization problem is called quadratic program because the objective function is simply quadratic and their constraints are all given by linear inequalities. And this is known as a type of convex optimization. And there is a theoretical guarantee that basically we have no local minima. So the optimization is quite easy, much easier than, for example, the non-convex optimization like deep learning. And there is a theoretical guarantee that we can always find the optimum points. And quadratic programming, QP, is a very famous class in convex optimization. So there are lots of solvers in standard library of optimization. So we can just download such software and apply their software to this problem. But however, in practice, there is a more special way to solve this type of problem. And for example, SMO, sequential minimal optimization, is a special method to solve support vector machine. And most of the library for support vector machine use SMO method algorithm. But I will not discuss here. Okay, so far I assume that two classes are linearly separable. But that's a very strong assumption. In most of the data, probably there is no such hyperplane to separate two classes. So that's too strong in practice. So in the development or in the already original paper of support vector machine, they consider how to relax this condition. And that is called soft margin support vector machine. Instead of requiring that all the points are separated by these two hyperplanes, we allow that some points may break this constraint. So instead of requiring this inequality, we allow that some points may take smaller value than 1. And the extent of breaking the condition is expressed by this Xi. Okay? And Xi, this one is non-negative, basically. And if it is positive, it breaks the condition. Okay, I can explain it in this figure. So this red point is within this hyperplane given by, Wx plus b, is it, in this case, -1 probably. And this one is within this region. So this breaks the inequality, this regressive inequality. So the Xi should be positive in that case. But if we don't assume anything about this value, we can allow any separation. Well, the hyperplane does not separate two classes at all. So this can take positive value, but we want to have a small value for this break of regress inequality. So we add this term to the objective function. We allow the break of the constraints, but the extent of breaking the constraints should be minimized. So this break should be small as possible. So this new term includes constant c. This takes a trade-off between the original objective function w squared norm of w and the extent of the break of linear inequality. And we want to minimize the summation of these two terms under the constraint of this new inequality, including the break z. Okay. This is called soft margin support vector machine, and we have new variable ci. However, this objective function to be minimized is still the quadratic function. This is quadratic part, second order term, and this is linear term. But including all of them, we have just a quadratic function again. And this part is also, we have three types of variable, w, b, and c, but still they are linear inequality. And the non-negative constraint also. They are all linear inequalities, right? Just a half of the space. So this objective function is again quadratic program. And we can solve it very easily by the standard library. Okay. So far, I have discussed only the Euclidean space. And I haven't talked to kernels at all so far. And all of these things can be kernelized. We can introduce kernel, and everything can be done on the feature space. That's the standard support vector machine, or nonlinear support vector machine. So in the case of nonlinear support vector machine, we have training data, but xi may not be a vector or arbitrary data, and we introduce kernel k, positive definite kernel on k, and consider the feature vector, as in the yesterday's talk. And let's consider the linear support vector machine on the feature space. Everything so far in developing the support vector machine is given by the linear function, which is basically given by the inner product between vector and the feature vectors and some vector in the space. So we can consider the linear classifier on the feature space. Instead of wx plus b, we have a vector h. This is a vector in the feature space, and the feature vector phi of x, and this expresses the inner product. This is just an extension of the Euclidean space to the feature space. This is our hyperplane on the feature space. And as in the previous case, our objective function is given by the norm of the coefficient vector, squared norm of the coefficient vector. Instead of w, we just write h here. And the norm is measured by the RKHS norm, well, the norm in the feature space. And this is exactly the same as the extent of the break of the linear constraint. And this is exactly the same, except that this part is given by the inner product of h and the phi of x, and I rewrite in this way by reproducing property. But this is the same as in the previous case. Okay, and we can do exactly the same thing as in the yesterday's talk. Actually, the solution of h is expressed in the linear combination of feature vectors by representer theorem. We can apply representer theorem to this case also. And after some work using the kernel trick, we can derive we can rewrite this objective function in terms of Gram matrix. This is a standard course of developing the kernel method. So this squared norm is replaced by this quadratic function. Sorry, I have forgotten to write the function form of h. H is given by the linear combination of feature vector, and the coefficient is given by ci. And this part can be also rewritten in the form of Gram matrix, and the coefficient is given by Cj. So we can obtain the objective function of nonlinear support vector machine in this way. And what we want to solve as variables is C and B here, and Z as the extent of break of linear constraint separability. Okay, this is again, given the Gram matrix, this part is Gram matrix. This part is the quadratic form given by the Gram matrix with Cj, Ci, Cj. And this is a linear term as in the previous case. And this inequality involves Gram matrix, but still this part is a linear function of Cj, and the other part is a linear in terms of B and Z. So this is again the linear constraints. So as in the linear support vector machine, the nonlinear support vector machine can be also solved by the quadratic program. Okay? And well, in quadratic program or in convex program in general, there is a technique to transform this problem to dual problem, and the dual problem has simpler form, and the people tend to solve the problem in the dual form, but I skipped the details about this. It takes too much time to explain. But anyway, in practice, we already have a very nice software to solve this problem, and we can use it. And another important point in solving the support vector machine is that we have some hyperparameters. So we introduce this new term and use C as coefficient, and this takes the trade-off between the original margin criterion and the extent of the break of linear separability. And this must be decided by a user. And also, we introduce kernel, and it is likely that the kernel has, well, some hyperparameter, like bandwidth parameter in Gaussian kernel, or in some cases, we want to choose Gaussian kernel, or Laplace kernel, or polynomial kernel, and so on. And in choosing the kernel or the hyperparameter in the kernel, the typical way is to apply the cross-validation. C and the parameter in the kernel are often chosen by cross-validation. And the standard library already implements the cross-validation part automatically. Okay. Okay, I explained the support vector machine starting from the large margin criterion. However, there is another explanation, interpretation of support vector machine. I quickly introduce it. So the support vector machine, especially the soft margin support vector machine, is known to be equivalent to some regularization problem. Well, our objective function is given in this way. But in some sense, well, we can erase this one and plug this one to replace this z by this inequality. And we can obtain, I skipped the detail, but we can obtain the equivalent expression in this form. This first term expresses some sort of loss function. So we have some nonlinear function given by the function space, feature space, and this part gives the value at this point, data point xi, and if this value is plus, and the the sign of this value is equal to the sign of yi plus 1 and minus 1, then that point is correctly classified, right? And this function, bracket plus, is this type of function. If this is negative, the value is 0. And if this is positive, this is, well, proportional, exactly the same as this value. So this function means that if if this one, let's say that yi is plus 1, and if this value is larger than 1, then the total value in the bracket is negative side, so the loss is 0. Okay? And if that is the original classification constraint given by the inequality, right? And if this value is less than 1, or let's say in the extreme case, if this value is negative, the classification is wrong. And in that case, we have a value larger than 1. So the loss is large. That's the meaning of this loss function. So this is different from the least square loss, but this can also express some loss of the classification in a slightly complicated way. And this is sometimes called hinge loss in classification or machine learning literature. And this can be applied to binary classification. And this part comes from the original objective function of the support vector machine. And this part, you may remember the kernel ridge regression has a similar regularization term. This is given by the squared norm. And this can be regarded as a regularization added to this loss function. So the support vector machine, in another interpretation, is the objective function of the SVM is given by some sort of loss function plus regularization. This is exactly the same as the previous expression. Basically, we swap these two terms, and this part is replaced by the hinge loss part. So maybe, well, we saw the similar figure in yesterday's talk in the part of kernel ridge regression. But in the case of kernel ridge regression, we use the squared loss plus regularization. But in the case of support vector machine, we have hinge loss plus regularization. Okay. Any questions so far? Okay. So there are lots of nice software library about support vector machine, and I show, I mean that the most famous one is libSVM. I think this is still maintained. Well, this has a very long history already. I hope that this link's still alive. Well, Chijelin is already, well, not in Taiwan, but yeah, I believe that there's, okay. Yeah, I guess so. So, well, this is a kind of, well, the toy problem given by JavaScript. So, well, I just want to play with that. Well, this gives the red one and the green ones are classified by support vector machine. And the C here is a parameter C to balance the trade-off between the constraint and the objective, large margin objective function. And this uses RBF kernel. And the sigma is a bandwidth parameter. We can adjust it. Well, maybe I plot. Okay, this is red point. This is green. No. Yeah, that's okay. That's okay. Yeah. So, for example, we have two classes like this, and if we control the bandwidth parameter, if we have a very smooth function, we have this type of classification boundary. If we have small bandwidths, which gives a very rough function, oh no, we have this type of classification boundary. And if we have smoother, then this may look like reasonable classification boundary, right? So the choice of the bandwidth parameter or the sigma in the Gaussian kernel strongly influence the classification boundary. And we need to choose the parameter very carefully. But fortunately, in the case of support vector machine, cross-validation does a very good job. So we can simply apply cross-validation to choose the bandwidth parameter. And we have this type of reasonable classification boundary. Okay, I just wanted to demonstrate that choice of kernel is very important in practice. Okay, maybe I come, well. Okay, here. So support vector machine is basically considering the classification problem, but nowadays the deep learning is very popular for classification tasks. So I'd like to give some comparisons between support vector machine and deep learning. So as you know that you have experienced deep learning, or you have already listened to a lot about deep learning in this research school also. And obviously in some problem like image processing, the deep learning gives a state-of-the-art performance. And however, the advantage of deep learning is most shown if we have a very large data set like medium. And in comparison, support vector machine is much easier to use than deep learning. In deep learning, we have many tuning parameters like architecture and learning rate and number of units and so on. And we need to optimize to obtain the state-of-the-art performance. And in the case of support vector machine, what we need to tune is basically there are two types of hyperparameter. There are C in the trade-off and the kernel, or the parameter on the kernel. So it's very easy to use. However, as I explain in the next section, that support vector machines are a little bit difficult to handle very large data like medium. We need some techniques, special techniques. And obviously the deep learning is, for very large data set, we need a very deep network, and the computation is very hard, and we typically need GPU. And the computation of support vector machine is much easier. And another advantage of the support vector machine is it's very easy to use for structured data like graph, strings, and sometimes probability measures. And as you may know that, the deep learning people are also developing some method to structured data like graph, and graph CNN is becoming, popular. But still, their performance is, not very bad, but not very high, actually. And another point is that in the case of support vector machine, we have a convex problem. So the analysis of the performance can be done theoretically. There are lots of works on the theoretical guarantee of the performance of support vector machine. But in the case of deep learning, because of the non-convex and the complicated behavior of the learning, it's not easy to analyze the performance theoretically. So there are pros and cons about the support vector machine and the deep learning. And people, some people try to show the good performance of a support vector machine in comparison with deep learning. And I show some example. This is taken from the very recent work appeared in PLOS ONE this year. And they develop a modular structure of the support vector machine using many support vector machines here by extracting the many linear combination of features. And after computing support vector machine with these many types of features, they combine the result in a linear way and to give the final result. And they apply this method to ImageNet and compare the result with the state-of-the-art deep learning method like AlexNet, GoogleNet, ResNet, and so on. And the performance difference is very minor, as you can see. Yeah, this may show some, the good performance of a support vector machine. But however, you may notice that the number of samples is very small, actually. The ImageNet contains more than 100 million in total. But they just use up to 80,000 But in a different view, we can recognize that with this order of the data size, there is no very significant difference between the support vector machine and deep learning. So if you have a small data set like thousands, there's no reason to tackle with deep learning and play with a different architecture. You can simply, well, use a support vector machine that may give you a competitive result than the state of the art. That's the message, yes.
So do you think this generalized to
Sorry? I'm not very sure. If the data size is larger, then we need to consider how to compute gram matrix. And I will come back to that point later.
Quick question,
Yes.
Why is the accuracy going down when you increase the number of training images? Like it starts from 97 and then it's become 95 and like less
Yeah.
net, for example.
I don't know. Yeah, that's true. That's strange. Maybe they include many classes. Maybe I'm not completely sure about that. So the number of classes in ImageNet is 1,000, I think, and maybe to increase their sample size, so they are not equivalent classification program. Yeah. Okay. So here's a summary of support vector machine. So support vector machines are basically proposing the kernel thing and the linear thing together in the original paper. And the linear method is already new, was already new, and that is called large margin classification. And we can kernelize it in feature space. And the nice thing is that as a result, the objective function is quadratic programming, which can be easily solved. And everybody can achieve the same solution, basically. That is quite different from neural network. And so so historically speaking, before support vector machine, there was a boom of neural network. That was the second boom of neural network. The current one is the third boom. And but people had a difficulty in tuning the structure of neural network and how to learn it. This is the same situation as the current one. And the support vector versions proposed and showed the competitive results to the neural network. And the people jumped into their support vector machine. And currently the pendulum swings to the, well, swing back, and deep learning is getting popular. And another one is, this one is not discussed in this lecture, but actually the solution, final solution is given by a linear combination of feature vector, but many of questions are zero. And the data points correspond to the positive, non-zero coefficients are called support vector. So this is a kind of sparse representation. Only part of the data point is used to express the solution. That is why this method is called the support vector machine. And the theoretical guarantee is obtained also, as I explained. Okay, this is the end of support vector machine. Any questions? Okay.
One of the concerns about SVM is the memory size, right? As the number of support vectors goes up, it can be very large very quickly. Do you have any comments on that?
But sir, well, to express this form, the memory size is linear to the sample size. That may be okay. Probably the difficulty is to express the Gram matrix. That is square. I will talk about that topic from now on. Okay. In kernel method, as we have already seen many times, the data, information of the data is expressed in terms of Gram matrix. So the Gram matrix has a size of n squared, where n is the sample size. So if sample size is like medium, then we have a matrix of million times million. That causes many problems. For example, we often want to compute the matrix inversion of the Gram matrix. But our matrix inversion or eigendecomposition requires n cubic. If n is million, that is impossible with our current supercomputer. And the memory is also very big issue if n is medium. So, but nowadays, the data size is very increasing, like million is very popular for images, for example. And the deep learning can handle that by, well, basically the stochastic gradient descent. But if we keep this Gram matrix, it's impossible to apply support vector machine to such a very big data size. And people have developed some techniques to solve this large size problem. And I will explain some of them. So there are two types of approximation strategy to Gram matrix. One is low rank approximation of Gram matrix. The another one is, this is also low rank, but a random feature. This is a slightly different approach. I will cover this one, these two. Okay, so we want to handle the Gram matrix denoted by K, and which may be very large, n times n. But in the first category of the method, they express this big matrix K by the multiplication of small matrix n times r. R should be much smaller than n. R times R transpose. So the rank of the right-hand side is at most R. That's why this is called low rank approximation. And this is closely related to the eigendecomposition. If eigenvalues are non-zero only at R eigenvector, for only R eigenvectors, then we can express by using square root of lambda, we can express the matrix K in this form, right? We can neglect many zero eigenvalues. So if the eigenvalues decays to zero quite fast, then we can neglect the very small eigenvalue and we can approximate K in this form. And fortunately, it is known theoretically in typical cases the decay rate of eigenvalues of Gram matrix is quite fast. So the approximation error in terms of low rank approximation, is quite small in that sense. So people use this type of low rank approximation if the sample size is very large. So there are a couple of, before going, well, I'm not going into the details how to construct this low rank approximation, but let's look at what is the advantage by this low rank approximation. For example, I use the method of kernel ridge regression to see how this low rank approximation is useful. The kernel ridge regression, the solution is given in this form. This is Gram matrix, and this is our identity caused by the regularization. And they are n-dimensional vectors. And this is a solution of kernel ridge regression. And this matrix inversion is problem if the size of K is very large, like medium. And let's say that we have low rank approximation in this way. Instead of using original K, let's use the small matrix R transpose. This is n times n, but the rank is very small. Yeah, this is K is replaced by this form. And we have lambda times identity, so we have a scalar vector here, a scalar matrix here. So approximately, we want to take the inversion of this matrix. But here is a very nice theorem. This is, again, the n times n matrix. This is just the approximation of n times n matrix. But this inversion can be replaced by R times R, the inversion of R times R matrix. Obviously, this is, if R is much smaller than n, this inversion takes only R cubic, and this should be much smaller than n cubic. And this trick is guaranteed by famous theorem called Woodbury, sometimes Woodbury, Sherman, Morrison, Woodbury, well, sorry, Sherman, Morrison, Woodbury formula. The matrix inversion of this form, given that the A is invertible, is equal to this way. And the crucial point is that, well, this part is R times R, not n times n. But instead, well, we need to multiply this part, R, and R transpose here. And this is R times R, and this is n times R. This is R times n. So we can recover the n times n matrix. And the computation here is simply R cubic plus R squared times n. So this is linear to n. So if n is very large and R is much smaller than n, this gain of the computational time is significant. Okay. And there are a couple of famous methods how to obtain the low rank approximation starting from the original matrix K. I skipped the details, but the famous one of the famous ones is incomplete Kleski factorization. Well, I skipped the details, but this is basically given by Gaussian elimination, which is probably within the standard course of linear algebra, to diagonalize a matrix, the method to diagonalize a matrix to solve the linear equation. And the computation of this algorithm, n times r square, and the memory is n times r, so everything is linear to n. And one important point is that, well, if we start from this the Gram matrix, this already has n times n matrix and n square already. But this algorithm doesn't start from this Gram matrix. But let's say that we have data, n data. And the matrix R is computed, the element of K is computed only needed. Only we need to call the value. So in total, the computation is linear, and the memory is linear to n. We don't compute everything at first point.
Sorry,
Yeah.
I have quick questions.
Yeah.
Why is the time is in R square? Because we calculate K because I have the n time R. It have the when we choose the n square R.
Yeah, the element is just n times R, but in computing the element, we
use a trick like
this is R, this is n.
this R.
Yeah.
Yeah.
And we have n times R element only. But in computing the element, we need R square operation.
R square operation times.
Yeah.
N should be n square because it's
n square?
we choose it's R. They have the R element to compute.
Yeah, but we don't compute this part. We stop this part. We stop this at this point. So we don't compute every element of this matrix, and the element is computed only required. Yeah.
Of the convolution.
Yeah, that's, yeah. Not necessarily symmetry, but, well, in computing R, we need only a part of the element of K. So when we need to that element, we compute it. In that sense, we don't need to compute all of the elements in K. That's why we have only n computational time and n memory. Yeah, that's a kind of important thing, that if we start from the matrix K, that requires already n square. That's not necessary. Okay. So another famous method is Nyström approximation. This is slightly different from the incomplete classical decomposition, but I skipped this one. And this is also linear to sample size n in time and memory. Well, another class of approximation is called random Fourier feature. Yeah, this aims at a very large data set, like more than medium. And this method uses the integral expression of the kernel. So, well, maybe I show the theorem first. Well, we have a very interesting integral expression with a kernel is shift invariant. The meaning of shift invariant is that the kernel, let's consider the kernel on the Euclidean space. And the shift invariant kernel refers to a class of kernel, so that the kernel value is given by a function of x minus y, like Gaussian kernel and Laplace kernel. Polynomial kernel doesn't satisfy this class, this condition. And for this class of kernel, it is known if we take the Fourier transform of the kernel in terms of x minus y, we have a non-negative function as a Fourier transform. And this is written K. This is writing K in terms of Fourier inversion formula. So this is like, well, in typical cases, like a Gaussian kernel, this part is a Gaussian distribution, and the inverse Fourier transform of the Gaussian distribution is again Gaussian. And in the case of Laplace kernel, we have a Cauchy distribution here. Cauchy distribution is the polynomial given by the 1/, square function of frequency, basically. Okay, I come back to this slide. And we have this type of integral expression of kernel. And the random Fourier feature use this expression to approximate the kernel function. So in the case of Gaussian kernel, this part is Gaussian distribution. So let's take sample point of omega. This is a frequency domain. By Monte Carlo sampling, we can take IID sample from the Gaussian distribution and approximate this integral in terms of Riemann sum. Okay, and there are low large number guarantees that this one is, if L goes to very large, this value is approaches to this integral. And this one involves their imaginary value, looks like imaginary value. But if the kernel is a real value, we don't care about the imaginary part, and we just take the real part. And the exponential I something is cosine plus sine. So if we break down this exponential I in terms of sinusoidal functions, this is simply this is our elemental mathematics. Cosine, cosine plus sine, sine. Cosine omega Lx, cosine omega Ly plus sine omega Lx, sine omega Ly. So in the end, we have a very simple approximation of kernel in this sinusoidal function form. This is random Fourier feature. And the point is that these omega are generated some distribution depending on the kernel. The form of the function approximation is always the same, but the omega depends on the original kernel. Okay. And this is, well, form is a very useful form, and we can actually express this final form if we consider this vector given by cosine and sine. The kernel can be approximated by the inner product of these two, the vectors for x and the vectors for y. So this is a quite simple approximation of the kernel function. And if we apply this approximation, let's say that we have kernel ridge regression. Then actually with this approximation, the objective function of the kernel ridge regression is reduced to the regression with the basis function given by this z function. So we worked on the feature space in some sense, but this approximation reduced the problem to the more standard nonlinear regression with fixed basis function given by cosine and sine. And the size of this problem is given by L, basically. So if the L is the sample size of this Monte Carlo sampling, so if the Monte Carlo sampling, the number of Monte Carlo sampling is much smaller than the original data size n, this method gives much more efficient computation to approximate the kernel method. So maybe I skipped these. Well, I'm running out of time, so I skip this slide. And I have shown two types of approximation. One is low-rank approximation, and the other is random Fourier features. And they are clear. They have clear difference in approximation. The first class of approximation, the Nystrom, the Kleski decomposition, or Nystrom decomposition, approximation depends on data. So once we observe data, we can apply this method. However, the random Fourier feature is an approximation of a kernel function, doesn't depend on data. So in some sense, that approximation can be reused to arbitrary data. But because it doesn't depend on the data, the approximation efficiency is less than the Kleski decomposition or Nystrom method. But for very large data size, people tend to use random Fourier feature, and that shows better results than the Kleski decomposition usually. And you may think that okay, we can approximate the kernel method or Gram matrix. But that approximation may reduce the performance. That may be a concern. But there are some theoretical analysis about the performance of kernel method with approximation. And if the approximation accuracy is high, meaning that the rank is sufficient, or the number of L in random Fourier feature is sufficiently large, we can actually guarantee that the final generalization error of the problem is not degraded by the approximation. The reason is that we are handling the noisy data. If the approximation has the lower impact than the noisy effect, then the approximation doesn't do harm at all. That is the reason. Of course, we need to take a sufficiently large rank or the random Fourier feature in that case, but we have some theoretical guarantee. Okay? Okay, so I'd like to show some results or some method of kernel for very large data set like medium. And it demonstrates that if we will apply kernel method to this type of, extent of very large data, the performance is very competitive to deep learning. So here is a very general form of kernel method. This can, if this part is hinge loss, this is support vector machine, and this part of least square error, this is kernel-related regression. We have some loss function and plus regularization term here. And as in the, for large data set, in optimization, what we should do is stochastic gradient descent, as in deep learning. it's not possible to, well, include all the training data at once. So people should consider the stochastic gradient descent for very large data set. And for kernel method, we can do that if this part is decomposed into the sum of the data points, like hinge loss, or support vector machine, or kernel ridge regression. And we can simply consider the gradient descent, but on feature space. And I skipped the details, but we can take the gradient in terms of functional vector f, and we observe that the kernel appears here. Okay, that's okay. And in this work, they propose to approximate this kernel in terms of random Fourier feature approach. And the random Fourier feature express a kernel in terms of sum of sine and cosine functions for L point of frequency. However, instead of considering the sum form, they propose, this is again the stochastic descent. They propose to take only 1 point of omega frequency to approximate this function. So this is a very, very crude approximation, but the philosophy of this is quite similar to stochastic gradient. On average, we can recover the kernel, but let's take one sample and make an approximation. On average, this one is equal to k. But let's take only one sample of frequency and use this approximation as a stochastic gradient descent. And by this way, they can handle the data set more than medium. I skipped this one. This is a comparison between other support vector machine method. So this is a comparison with this, what they call doubly stochastic gradient descent for kernel method with deep learning. And they used 5 famous data sets, including continuous output and classification task. And basically, red one shows doubly stochastic gradient. So the kernel ridge regression or support vector machine, depending on the continuous or the classification task. And the blue one is neural network. And the green one is actually, I don't remember correctly, but the joint trained neural network. Sorry, I don't remember this one. But basically, the green ones shows worse results, so I skipped this one. And compare the red one and the blue one. The red one is their proposal for kernel method. And there are 3 top figures show the classification task like MNIST, Cypher10, and ImageNet. And they use it's not very clear, but more than medium. This is medium, 10 to 6. So I guess they use something like 10 million data. And you can see that for small number of training sample, the kernel method is significantly better than the neural network. But it seems that the neural network can handle more data, and if the data size is increasing, well, but still the red ones are shows very competitive result to neural network. And the bottom 2 figures show the continuous output case, kernel ridge regression basically. And in this case, the kernel method shows much better result. And in this case, neural network shows slightly better result. So these figures show that if we make some nice approximation method to handle the very large scale data, the performance of kernel method and deep learning are quite comparable. Okay. Any questions so far? Okay, and in the remaining, well, maybe the 10 minutes, I will quickly show some of the structured data, which, well, sometimes called non-vectorial data, but structured data is also a popular word. Sorry, perhaps I cannot cover all the slides, but I talk some of the contents. So one of the advantages of the kernel method is a very easy extension to non-vectorial or structured data. Once we have kernel on such data, that we can, well, easily apply just any kernel method to such data. The only thing we need is a kernel defined on such data. Okay, so the typical structured data are string. String is a sequence of some alphabet. And this is, well, typical example is language, but the language processing is, well, perhaps it uses, well, the many clever techniques. So the typical application is a DNA sequence or RNA sequence or protein sequence. And well, text is another example, but perhaps in recent natural language processing, the kernel method is less popular than the word-to-vec or some vectorization of the words are very popular in natural language processing. So it's a little bit obsolete. And graphs. So the chemical compound can be typically expressed by a graph, and people consider some kernels for graphs. And path tree is also another example, and this is, well, already a very classical work, but people consider the kernel for trees and apply it to their path trees. That's also possible. I skipped the details about how to define kernel, but basically they consider some substrings in a sequence or in a word and consider the matching of such substrings in a word. In words, sorry, 2 words. That defines the kernel value for 2 words. Well, in this example, we have several common 3, in this case 3, that can be arbitrary number. Like STA can be found in both words, and then we make a flag to such common substrings and consider the inner product of this one, basically, and that computes our kernel. And this type of kernel was very extensively studied in, let's say, more than like 15 years ago. And the one of the concern is the computational cost. By straightforward computation requires like square or cubic sometimes, and that prohibits the application to a very large data set. But by some clever way, people, well, in some cases, people developed their method linear to the sample size. And we can, for example, consider the PCA for words. But nowadays, perhaps words can be expressed on the vector space, so this is not very surprising at all. But this is just like a historical well, topic, maybe. Okay, I will show some, well, just a quick explanation of kernel method for handling probability distributions. Perhaps you can ask Krikamola about the details. He's an expert in this field. And well, we have many statistical problems to solve. And in the end, well, statistical method considers the inference on probability distribution represented by data. And the kernel method can be extended to such probability distributions. We can regard that the probability distribution like data in some sense. Well, in kernel method, we often consider the feature vectors given by some data point on the feature space. But in this methodology, we summarize the distribution of the data on the feature space by a single vector given by the mean of the distribution on the feature space. You may think that by considering only mean, the information is significantly reduced and we lose many information. But that is not true, because in this figure, we have only 3 axes, and so the mean has only 3 values, right? But the feature space may be infinite dimensional. That means that we have infinite number of axes. So the mean contains infinite number of values. For that reason, we can include all the information of the probability distribution to the means. That is one, well, crucial point about considering the mean on the feature space. Actually, for some class of kernel, like Gaussian kernel or Laplace kernel, we can prove that we don't lose information by taking mean on the feature space because of the infinite dimensionality of the space. That is one point. And another point is that mean can be computed very simply. We have feature vectors, and just take means. Means is just given by the empirical mean in this way. That's very simple. And for example, I skip. Yeah, if you are interested in this topic, well, Krikamola has written the monograph, and you can, well, everything is written in this book. Anyway, so for example, we can easily compare the difference of 2 distributions. So this is called maximum mean discrepancy. We have 2 data sets, or 2 distributions, P and Q. And let's compute the mean for P and for Q, or we can estimate these values by the empirical sum of feature vectors that is written by m hat P and m hat Q. They should be very small if P and Q are identical, and they should be very large if P and Q are very different. And we can use this value as the distance measure of 2 distributions. And we can, for example, apply this idea to, not this one, sorry. Yeah, 2 sample tests, which concerns the test of the, this one want to determine whether or not 2 underlying distributions are same or different. Or we can consider to test the independence of 2 distributions, 2 random variables, by comparing the joint distribution and the product of the marginal. That's a definition of independence, right? So we want to compare the joint distribution and the product of the marginal. And that can be done by this kernel mean approach. And in another and recent application, they use this distance measure for distribution to implicit generative model, which is similar to GAN or variational autoencoder. This can be applied to this kernel mean approach can be applied to generate sample from some distribution given by training data. The application is quite simple. We have data, and we can compute the kernel mean for data, like face images. And we apply, we prepare the deep neural network here, and Z is the sample from the standard distribution, like Gaussian distribution or uniform distribution, and we transform the points to by deep neural network, and we obtain some sample. And the goal here is to have very similar sample to the original face images. And we have a parameter of deep neural network, and we just minimize the parameter so that this maximum mean discrepancy is minimized. So people have, yes. No, in this formulation, no discriminator. Yeah. And people are trying to include some sort of discriminator here, and that improves the performance. Yeah, but the original form is just given in this way. We don't need discriminator. In another sense, discriminator is already solved in the form of norm. Yeah, okay. Well, this is almost the end. So we can also develop some Bayesian method using the kernel mean expression of probability distribution, but I skip all of them. Okay, I skipped some application also. So this is the end, and yeah, this is the standard textbook of the kernel method. If you are interested, you can look at this one. And I provide some references about some topics, not all, but some topics. So you can look at these papers if you are interested in more. Okay, this is the end. I check your questions.
I'm trying to understand your application, like using the kernel model, and for example, I mean, if we are focusing on different, how to say that, different, like for example, we want to use the image to encode the kernel with the map, and I cannot imagine that how to, for example, we think about the language processing, like the text. So how to use the feature map from the text to the feature map.
So you are asking how to define kernel, for example, for text or image?
I'm not going to take care about define the kernel, but I'm considering about how to encode from for example, we have the many X, right? One example, so we have the multiple features, and I don't know, so we want to talk later.
Okay, I see.
Hi. It seems to me that choosing the right kernel is very important.
Yes.
And it is unclear to define or choose one given data. One thing is that how to choose, and second is it possible to define a valid kernel from data alone? I mean, like learn from it.
So it depends what kind of kernel method you are trying to use, and for supervised learning, like support vector machine or kernel rate regression, I recommend to use cross-validation to pick up one parameter in the kernel. Yeah, that's obviously the testing the to the with the validation data and simulates the test performance. So the cross validation is the best way to do, so there are many other methods to learn the kernel or parameter in the kernel. Now, some people try to use deep learning approach to learn kernel, for example. And there are lots of recent works how to learn kernel in a more complicated way. Or some people consider the layered structure of kernels and so on. Yeah, so there are lots of methods proposed currently to learn kernel from data. And for the second question, yes, we can learn kernel from data. And of course, there are many problems like to prevent overfitting and so on, like in deep learning. But basically, we can learn kernel from data. That's perhaps a more recent advances with kernel method.
I have a question. In the present, what is the ongoing research or main research in this field?
Main topic.
Main
Main topic.
Ongoing research in this field.
Ongoing research is probably how to learn kernel in a better way. Yeah, that's one topic. And another, more recent interesting direction is to, deep learning, how to combine, in some sense, how to theoretically combine deep learning and kernel method. Some recent works consider the deep learning in terms of kernel method in the limit of the number of units. And if the number of units goes to infinity, it can be represented as a Gaussian process. This is a Bayesian approach in terms of kernel. And we can write the learning behavior of deep learning in terms of kernels. That's a very interesting direction. That's very recent work. So the people in the very frontier of the research, people are looking at how to merge, or how to make a framework including both of kernel method and deep learning. Yeah, that's I think an ongoing research direction.
I have a question for the GANs example that you show. I'm not quite sure about how it actually works and what is the difference between this example with the standard variational autoencoder, because it's for the equation here is quite like the VAE, because the objective function is try to minimize the loss function. So I'm not quite sure what is the difference.
Perhaps this is, rather than variational autoencoder, this is closer to GAN, I think. In the case of GAN, we have some divergence, like Jensen-Shannon divergence as a criterion, but it cannot be computed, and they introduce the discriminator to approximate the objective function to compare two distributions. But in this case, we can easily compute the discrepancy between two distributions. And so we have only the generator. We don't have discriminator here. However, one weak point of this original approach is that we need to fix kernel. By fixing kernel, we are basically defining some smoothness, assuming some smoothness of the function or the discriminator in this case. So the people are trying to prepare much a wider class of kernels and pick up a good one to make a discriminator in some sense. Yeah, this is a little bit, well, that's theoretically involved, but we can assume that some sort of discriminator in this form to express the norm in a variational way. And specifying a kernel is equivalent to specifying a smoothness of a discriminator. And some people try to combine the discriminator to improve the performance of this one.
All right. So for this one, we have to pick the kernel first in order to map the data into the feature vectors to the mean this one, right?
Yes.
All right.
Yeah,
Thank you
that's
so much.
what this is doing.
So probably let's take the remaining question offline. So I think that conclude the kernel session. So I think I can count I think approximately 5 exercises in the lecture. Anyone here who already finished the exercises? Yeah. So I hope you spend some time trying to understand the topics and also the finishing all the exercise that Kenji gave. So I think this is really nice opportunity for everyone here to learn about kernels and also so Kenji is basically at the one of the researcher at the frontier of kernel method, and it's our pleasure to have Kenji here. And thanks a lot for your time. And I hope next time we can organize the whole research school on kernel method, because I feel that we don't have enough time to talk about this topic. And so I think for everyone, I hope that you learn sort of another angle of machine learning, because nowadays deep learning is very popular. And so this is another aspect of machine learning that I think also have a very potential for future research. Okay, so we have a small token of appreciation for you. Thank you very much for coming, and let's thank Kenji again.